My name is Reza, and I'm from Monash University, the same place where Ray comes from. So I'm going to talk about some machine learning techniques for natural language processing. And the disclaimer is that this is my biased, collection of papers in this area. So if there is a work that I'm not talking about, it doesn't mean that they are not important. It's just, I have tried to select a subset of works that I've thought we might be able to cover them, in the short amount of time that we have. So I'm gonna present, according to the following outline. And let's start with the introduction. Application of text models are everywhere, like, from social media to intelligent assistants to translation, etc. So NLP is nowadays especially a hot area of research and also in industry. So briefly speaking, natural language processing is the branch of computer science focused on developing systems that allow computers to communicate with people using everyday language. So the focus is on communication here. So the definition comes from the Juravsky and Martin's textbook on speech and natural language processing, which is a great book and Bible if you are interested to know more about the topics. So the classical and modular approach to natural language processing, focusing on, let's say, dialogue systems, is the following. So we start from the sound waves, and then there is, an acoustic processing being done, and the output of that is words. Then those words go to the syntax module, and then the parse trees are produced to show the syntax of the sentence and to which these words belong to. Then, the syntactic tree is given to the semantic parser, and that gives us like the meaning representation of the sentence. Then that gives to the pragmatics module, and the contextualized meaning is produced, and then the result is sent to the rest of the pipeline. So this is a classical and modular approach to natural language processing. And as I mentioned before, if you're interested to know more about each of these topics, please feel free to have a look on the speech and language processing textbook. So let me explain a bit. So basically, this slide shows what I mentioned before about the syntax, semantics, and pragmatics. So syntax is concerned about the proper ordering of words and the effect of it on the meaning. So you see basically here a few examples. Semantics is concerned about the literal meaning of words, phrases, and sentences, as we talked about before. And pragmatics, is related to the contextualized meaning. For example, the ham sandwich wants another beer. That wants, like, there is a speaker to which this sentence is referred to, and etc. So the meaning representation based on the context is the subject of pragmatics. So each of these topics are covered in depth in that book. So just to give you an example of a syntactic parse tree. So there are these two sentences: I ate the spaghetti with the chopsticks, where the chopstick actually is attached or describes the verb ate. Whereas I ate a spaghetti with the meatballs basically is describing the spaghetti, right? It's attached to it. So that's a classical ambiguity case in syntactic parsing, referred to like prepositional attachment, whether it's the verb phrase or the noun phrase. So in syntactic parsing, the main focus is to come up with the correct syntax tree and disambiguate the possible ambiguity that might be there. So in semantic parsing, a natural language utterance or sentence is mapped to a logical representation, that logical representation is then executed on a database or whatever whatever the task is. So for example, I mean, we might have like a database of cities and etc. in the US, and we may want to map English database queries to Prolog and then execute the Prolog onto the database to get the result. So this appears whenever we want to interact with a database through natural language. That's an example of the semantic parsing usage. And then we go to pragmatics, like the contextualized meaning. So a classic of contextualized meaning and important elements in that is like anaphora and co-reference resolution. For example, John put the carrot on the plate and ate it. The question is that whether it refers to plate or the carrot or maybe both. So that is called anaphora resolution. So we want to find out the name entities to which or these pronouns or like this it refers to be able to understand the meaning of the sentence. So these are the subjects of pragmatics, and I don't go into the details of it. So this is pretty much the classical NLP. And what I want to cover is, the new wave of the neural approaches to natural language processing. So, and in that, I'm going to focus on large pre-trained language models. So the neural approach to NLP tries to, whenever possible, merge like a few modules in this pipeline in the classical NLP that we talked about before into one module. So, ideally replacing all of the modules into one end-to-end system. The workhorse of doing that is, as I mentioned before, neural language models. I jump into the different kinds of neural language models that are out there. It is not basically, a exhaustive list. I only cover like a few important architectures. Like for natural language generation, the primary architecture is referred to the class of neural decoders. So for example, whenever we are interested to generate like text, this is something that we might be interested. In for natural language understanding, which is not generation, it's basically understanding. There is an already existing text and we want to understand it. The class of architectures used for that are referred to as neural encoders, and this is, for example, useful when we want to build a system to predict the sentiment of some reviews, for example, and do sentiment classification. And another type of architecture which is good for natural language understanding and generation is referred to as neural encoder-decoder models. So the encoder part understands and the decoder part generates text. So, and this is useful, for example, for machine translation. They want to translate, let's say, from Chinese to English. So we want the encoder to understand the Chinese and then the decoder to generate the English as the translation. Okay, so what is good about these neural language models or these different architectures is that, I mean, with a slight abuse of language, I basically refer to all of them as language models. But it does not necessarily mean that they are used for generating language. Sometimes they are used for, language understanding as well. So let's use the language model terminology to refer to all of them. What is good about them is that we can actually train them based on the existing and available corpora, on the web or on resources such as social media, etc. So why it is important? The important is that once we kind of in a self-supervised manner train these models on the freely available data, then, for a target task of interest, we may not need to have a lot of annotated data. So that's primarily a mechanism to reduce the effort needed to prepare label data for many problems. And as a side note, that's one of the bottlenecks in today's AI, like, how to, reduce that bottleneck, the data annotation bottleneck. In this approach is by taking, these language models and train them on a lot of synthesized label data, which we refer to as self-supervision. And then once we pre-train them on this data, we can then use them for the target task of interest with few labeled data. So I talked about language models, but what are they? So imagine that we have this peculiar creature telling something like, named must be your fear, before banish it you can. Like it's a sequence of words, but as human we cannot make sense of it because the ordering is not good. So so let's reorder, those words in that sequence. Named must be your fear, before banish it you can. As mentioned before, it is not a good English, but let's reorder them. Your fear must be named before you can banish it. Okay, so it's a good English. And the job of a language model actually is to understand what sequences of words are good English and what the sequences are not good English, right? So to model kind of natural language. Why language modeling is important? Because it has a lot of applications. For example, in speech recognition, like if you want to convert like waveforms, like wave speech forms into transcriptions, we might have different options, and we use a language model to choose the good one, the one which is fluent. In automated translation or machine translation, the same. Like for like a source sentence like this, we might have two candidate translations, and a language model gives a higher score to show the plausibility of the more fluent sentence. And also in predictive typing, as soon as you write a prefix, for in auto-completion, a language model can help with that as well, to suggest what kind of words or phrases that can be out there to complete this prefix. Okay, so language models are important in terms of the application as well. But there is another crucial property of language models, and that is language models do not need labeling effort, right? So as a task to train model for, language models, all they need as data is the existing available text. They don't need additional labeling, and that property actually makes them very, very interesting for our purpose, which is training these large neural models without annotation effort. Okay, so let me jump into how we can train, or let's use the terminology pre-train these different architectures that we talked about so far, like decoders, encoders, and encoder decoders. For each of the architectures, I'll discuss the self-supervision task, which is used for parameter optimization, which is basically a variant of language modeling idea that we have seen so far. So let's jump into decoders. The objective function to train a decoder model is predicting the next word given the prefix. Okay, so predict the next token condition on the previous tokens. So and the model needs to give high probability to the correct word given the prefix. So training and inference is done autoregressively. Autoregressively means like, one word after another. It can be from left to right, or it can be from right to left. And in, these kind of models, once trained, they are very good for generating text. So yeah, okay, let me go into the most prominent version, model from this class, which is the GPT, like generative pre-trained transformer. So it has 12 layers like of transformer decoder. My assumption is that you guys are familiar with the transformer encoder and decoder. So it has like 12 layers of transformer decoder. The tokenization is done by bypair encoding. It's basically the detail. But the important thing is that you have these transformer block, like TRM blocks, and E1, E2 to En are kind of the words or the tokens. And then given each prefix, the objective function is for the is to produce like the word for the next time step, and that's the objective function. So GPT or language models, decoders are really good for generating text. For example, if you go to this link, you can try it yourself. So what we can do is that we can give a context, like, which is, some sentences, and GPT condition on that can generate the rest of it for us. For example, the context can be in a shocking finding. Scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. So this is the human provided context. And then the rest is like GPT generated text. The scientists named the population after their distinctive horn-oved unicorn. These four-horned, silver white unicorn, etc. So you can actually go through it, and the text is not that bad. It is not perfect, but it is it is okay. There are like drastic failures as well, but there are good cases as well. So the importance of GPT is not only the fact that it used like big transformer decoders, decoder models to learn language modeling on large amount of monolingual text. It's not only that; it's also the fact that a series of papers at GPT 1, 2, and 3. They did interesting things with the trained language models. So basically, what the main idea has been to unify different natural language processing tasks into one format, which I will describe shortly, and then solve all of them with this one model. So in like GPT-1, for example, the idea was following. So the input is represented as a long sequence containing special tags. For example, if you have a paragraph, the special tags might be the limiters, to separate like two sentences. So you put all of the sequences in one sequence, in one super sequence, and you give it to the GPT model, right? And then and then you get the the hidden, like one of the states from the GPT kind of neural network as the representation of that long text, and do whatever you want and use it to do whatever you want to do. For example, if I have like a review for a product, like which has multiple sentences, I can concatenate all of them, give it to GPT-2, and then I can get the kind of the hidden states of the last layer of the GPT-2. and kind of get the average of them, or to get the representation, a fixed dimensional representation of the review, based on which I can then do the prediction for the sentiment. And then like they use the same philosophy for like textual entailment, like which is another task as well, with, involving two sequences, two sentences, right? So they wanted to say whether like these two sentences contradict each other or don't, for example, in a kind of simple description. So they basically use the same method for solving this as well. So if you want to also determine whether two sentences are similar or not, like which might be interesting for information retrieval, like you want to basically measure the similarity of the query against like the web documents, for example. You can do the same thing as well. So we can basically encode the documents on the web by GPT-2, like and store the vector representations of them. And then whenever like there is a query, you on the fly compute the representation of that query, and then match it against the kind of database of representations that are out there representing the documents on the web. And we can use it for question answering as well. So just to summarize, that's one of the important messages of this paper, of this series of paper as well. Like if you read it, I think noticing that they try to attack many NLP problems based on one model is in itself an interesting idea. Like maybe nowadays it is not, but in the beginning it was a big deal. So not only that, there was this concept of prompting, which is also very interesting. The prompting idea is is the following. So you provide, actually, when you train the language model, like GPT language model, so what you can do is that, let's say you want to do sentiment classification, right? So they say that you don't need to build a sentiment classifier for, but by adding a classifier on top of the GPT-2 language model representation. So what you can do is that you can consider like, the GPT model as, as your inference engine, right? And then provide it with the, or condition it, prime it on the data, on the, review paired with the labels, right? And then, GPT, on the fly learns from this natural language kind of training, way of training, learns like, the concept that needs to be predicted for, a new review in the test time. So there is no training needed. So all you need to do is to provide the instances in the training set to the GPT model, and use it as a condition for like the document for which you want to do the prediction. And GPT learned like magically from this natural language supervision, what the prediction task is, and does the prediction for the X that you're interested in. So for example, in here, we can say that the gray text is the training set that is provided to GPT. In here, like the purpose was to use GPT for kind of distinguishing good English from bad English. Like it says poor English input, like I ate the purple berries, and good English output is I ate the purple berries. So it has learned how to kind of get the poor English, and it has been given the information what is an example of a poor English sentence and what's an example of a good English sentence. And you provide a few of these, and then you provide a poor English sentence, and then it learns from those examples to provide or predict the good English sentence. And the same strategy can be used for machine translation and other tasks as well. You are very welcome to look at the paper. And the concept of prompting, which comes from this paper, is actually really, really interesting and important. I need to correct myself. There might be other works like before this paper which introduced prompting as well. So I'm not claiming that this is the first paper for that, but they showed that by prompting, which is the process that I just described, you can actually learn with only a few labeled instances a very good classifier based on the large language models. And if you are interested to know more about prompting, this is a good survey paper by Graham Nubik in CMU, and you are welcome to have a read through it. Okay, so having discussed the decoders, let's go into the encoder models. Encoders, in the encoders, the input is encoded into a contextualized embedding. So the purpose is not to kind of generate text. Some variant of pre-trained encoders like BERT that we'll see shortly also provide sequence embedding and pair sentence embedding, like embedding to kind of encode single sentences or paired sentences. The training is bidirectional, and the model sees the whole sentence, like the past and future. We'll see shortly, like it's as opposed to decoder-like models where when we train them, in the training we only consider like the past tokens to kind of predict the next token, but in BERT, like the past and future can be used, or are used to predict the the words or tokens. So before I go to BERT, which is the prominent model in this area, let's take a step back and look at Elmo. Elmo is similar to it basically is a very interesting encoder. They came out with BERT roughly at the same time, I think in the same year. Elmo is based on like stacks of LSTMs, LSTM language models. So you have like a LSTM language model from left to right that you see here. You have another one from right to left, like given the right context, predict the next word before it. And then these can be, these language models like bidirectional, based on bidirectional LSTM, left to right and right to left, can be stacked, as I mentioned before, like L layers. And then you concatenate the, left to right and right to left representation from the top layer and consider that as the embedding of the input tokens. So the input tokens are E1, E2 to EN. And the embedding provided by the model is T1, T2 to Tn, right? So at the time, it was like a very interesting development compared to the GPT that we saw before, because GPT was like one direction, like one direction, like from left to right, but and that is used for language modeling, right? Language generation, and it made sense. Like for language generation, you have to start from like one direction, or maybe not have to, but that was the motivation of those people. But for text understanding, we are not generating the text. The text is given to us, so we can go from left to right and right to left to have like bidirectional LSTM, and this is what these guys did. So after this, what basically happened is that people asked like two questions. The first question is that what if we replace LSTM with like the newly at the time introduced and more powerful neural modules called transformers. What if we basically replace LSTMs with transformers? And what if, like, the prediction task is not the language modeling objective? What is, it's the mask language modeling objective, which I described here. So in mask language modeling, we do the following. So here is an example. You have a sentence like, Jim made spaghetti for his girlfriend and he was very proud. So in that sentence, you randomly select some words, spaghetti and he, for example, and replace them with a special token called mask, right? So think of mask token as like a variable that the model needs to identify its value. So each of these mask variables, have the domain of those variables is the words in the vocabulary, and the job of the model is to solve these puzzles, like when given Jim made mask for his girlfriend and mask was very proud. The job of the model is to predict the first mask is spaghetti and the second one is he. And as you can imagine, like the model learns a lot of things about understanding natural language this way, right? So for example, in here, in the case of he, it needs to kind of learn about coreference resolution, right? Anaphora that we discussed before, to kind of solve this puzzle, right? So it learns those skills during the training. All right. So this is the objective, and that's the architecture. And here is where BERT born, how BERT was born. So BERT stands for bidirectional encoder representation from transformers, and the process is what I mentioned before. You have these stacked transformer blocks, transformer encoders, and then you have the mask language modeling objective, and you train the model based on a lot of text, right? And then you can use it for representing or understanding the meaning of new sentences. The crucial thing is that in the mask language modeling objective, these puzzles are made kind of without any effort, human annotation effort. Like it's easy and kind of cheap to synthesize these ones, and train the model with a lot of available text. Okay, so in the original BERT paper, they used as the corpus, they used the Wikipedia and the book corpus, and they use a dictionary size 30K for tokenization. And they actually train different models with different sizes. You can go into these resources for TensorFlow and PyTorch implementation of these models. Okay, let's look at BERT in more details. So the input sequence is my dog is cute. You add a special token called CLS to the beginning and a special token SEP at the end, right? SEP is a special token that specifies the end of the sentence, and CLS is a special token whose representation in the output is supposed to represent the meaning of the whole sentence. Okay, so you have this input. So what they do is that they represent each token in the input by an embedding coming from an embedding table. Then they add, these are the E rows here. Then they add these, these positional encoding E0, E1 to E5 here. Like, each of these E's actually represents the embedding of a position 0, 1, 2, etc. And then they also add like a sequence embedding, like in here, like we have one sequence, let's call it A, like my dog is cute, And then, they add an embedding for the sequence as well. This is necessary or becomes interesting and useful when we have, let's say, instead of one sentence, we have two sentences. So then, like for the first sentence or sentence A, we have an embedding for E, for the sentence A, and then for the words of the second sentence, we have another embedding called EB, like the sentence B. Anyway, so these are these are what the positional embedding, token embedding, and sentence embedding. These are vectors which for each position are added up, and then we have one vector for the input in the transformer. And then, as mentioned before, and the training objective is the mass language modeling. Now, once that model, the BERT model, is trained, how we can use it? So, for example, in sentiment classification for the reviews. So imagine that we have a review like whose words are V1, V2 to Vn. We put CLS in the beginning, SEP, and then SEP at the end. If it has multiple sentences, we will have like other words and separator tokens, as well. So we pass these super sequence through the BERT, and at the end, we look at the embedding of the CLS token, and that embedding is capturing the meaning of the full review, and then we can use it to build a classifier. For example, to put a probability distribution over the two labels like positive and negative. This way. So we multiply this representation O by the output representation O by W, and then add this B, and then pass it through a softmax to give us a distribution for the prediction of the class label. And then using the labeled data for the sentiment task, what we can do is that we can actually train the parameters of this classifier W and B. The classifier can be more involved as well. This is a simple classifier. The same principle applies when we want to encode multiple sequences. So this is like similar to the case of one sentence, but when we have two sentences, like for all of the words of the first sentence, we have EA, and for all of the words of the second sentence, we have EB, right? And as you can see, like the two sentences are separated by this SEP token, okay? And then like the CLS token, which is in the beginning of this paragraph, its embedding, like in the output, represents the meaning of the full review. All right, and then you can use this output embedding to do whatever you want to do with it. Build a classifier, for example. All right, so these are like the different tasks that in the BERT paper they tackled using the same approach that we saw so far, like taking the embedding. So I don't go into the details of it. You can look at the paper for more details if you are interested in. So here is an example of what's happening in multi-head attention in BERT. So if you recall the transformer architecture, it has multi-head attention in it. So the multi-head attention actually learns to to pay attention to parts of the sentence which are important to understand the meaning of a particular word. For example, this word "it's," like to understand the meaning of "it's," like the attention heads in BERT have learned to one of them has learned to look at the law, and that does like coarse resolution. It seems like let me read the sentence. The law will never be perfect, but its application should be just. This is what we are missing, in my opinion, right? So it's actually refers to law, like obviously, right? So and then the Bear's model has learned, like through this through the attention from this head, that this it is related to the law, right? And there are other examples by looking and inspecting the attentions as well. So the shorter story is that there is a lot of linguistic information encoded in these attentions, which is basically reflected in the output representation that we get, to represent the meaning. So those, the meaning that we get has a lot of linguistic information in it. So let me look at a few papers which improved BERT. So one of them is called SpanBERT, like instead of randomly masking tokens, as we did in BERT, they try to mask spans, like tokens which are close to each other, and then reconstruct or maybe predict them in the training time. So as you can imagine, this is a more challenging puzzle, or in the training time, for the model to solve in the training time, right, than just individual tokens. And intuitively, it should mean that it should lead to a better natural language understanding or encoder model, which indeed is the case based on these tasks that we see, like news QA, trivia QA, like these are question answering tasks on the in different columns. And then you see Google BERT, and the BERT implementation of this paper, and then the SpanBERT, right? So the SpanBERT has led to better classifiers for these question answering tasks, and this is the average of those ones as well. For more information, you can look at that paper. I think this is one interesting extension that one can imagine immediately, right? There are a lot of things, but this is like one of them. And this is another interesting extension over the BERT paper. So what they did is that actually they very cleverly changed the supervision task, and the idea is really interesting. I mean, let me mention what's happening, and then we look at the the motivation. So what they do is the following. So imagine that the sentence is the chef cooked the meal, right? So what they did is that, like BERT, they randomly mask a few tokens, mask chef, mask the meal, and then they gave this masked sentence to a to a very kind of a small BERT model, let's say, and then ask the BERT model what you predict for each of the masked tokens. So the masked tokens they are replaced by this generator by some words which, according to this generator, may make sense for those positions. So, for example, the first mask is predicted. The word predicted for it is the, and the second one, ate. So the chef ate the meal. That is the imputation of the generator for the input sequence. And then like the language model that that we are ultimately interested in to build is this discriminator. Why do we call it discriminator? Like the training objective to train this large language model for each position is to say whether the input token has been the original token or it has been an imputed token generated by the generator. So first of all, this is a very kind of arguably this is more difficult. Like solving these puzzles is more difficult than the BERT puzzles, right? So for each position, the language model is expected to mention whether the word in the input has been the original one, or it has been, the one imputed by this generator model. So the first one is original, the second one original, and then it has to learn or distinguish that the third one, 8, is not the correct one. So it's a replaced one. So okay, so the puzzles are more difficult. That's the first observation. And the second observation is that the supervision signal is dense. Like, what do I mean by dense? Like, the model needs to make a decision about original replaced for each and all of the tokens of the input, right? Whereas if you remember for BERT, like the training objective only consisted terms corresponding to the mass positions. So it was kind of sparse. So it's a very kind of dense supervision compared to that. And then, like, they applied, basically they applied this supervision to kind of train BERT models, which are, encoder models, which are smaller, which are smaller than their BERT counterparts, but more accurate. So, and we can see, like, an example in this table from the paper as well. So this is like an example of a paper showing, like, that these auxiliary tasks can be kind of synthesized and built, in a very clever ways to outperform the kind of the mass language modeling objectives used in BERT. There is another paper called Roberta, and Roberta is basically a paper about how to train BERT fully and properly and in a very robust way. So what they did is that they took, like, the data used to train BERT based on the mass language modeling objective, and then they increased the number of optimization steps. Like, so instead of 100K, go to 300K and 500K. And then as you increase the number of optimization steps, they show that you get better performance on the classification tasks. So that shows that better optimization on the encoder translates to better understanding. Models that can better understand. Okay, so that was Roberta. There is this paper as well that I think is very important, and this paper says that it says the following. So it says that if you want to take a large language model as the encoder of your system, which is the backbone of your system, on top of which you have your classifier, right? So this paper says that when you train this system on the target task of your choice, for example, in sentiment classification, it is not only necessary for to train the parameters of the classifier on top that you have newly added, but it is also usually a good idea to kind of further train the parameters of the large language model, right? So instead of freezing the parameters of BERT, for example, as it comes out of the box, it is better to further train it based on the data of your target task of interest. And this becomes more important if the domain of the task, the target task that you're interested in, is different from the domain of the data based on which BERT has been trained. So if you look at this paper, they look at these different domains, biomedical domains, like reviews and etc. And they show that particularly when there is a need for kind of domain adaptation from the domain of text on which BERT is trained to the domain of text for which we want to build a classifier, it's better to kind of let the parameters of the backbone language model or the encoder to be further updated and fine-tuned as well. And that further fine-tuning actually is a mechanism for domain adaptation. It's a very kind of easy and straightforward mechanism for domain adaptation compared to many more complicated ways of doing it. And usually it works, really, really good. Okay. Okay, so let me move on to encoder-decoder models. So in the encoder-decoder models, we have an encoder which encodes the input, and we have a decoder which generates the output. Think of machine translation. So we want to kind of train such encoder-decoder models. All right, how can we do that? So one way to do that is the following. So note that before I go to how we can do that, note that one of the requirements in the training is that we shouldn't need any data which requires human supervision or human annotation, right? So we don't want to have that, and we want to kind of train the model based on the existing available and freely available and cheap text, maybe on the web or in other from other sources. So one idea is to train this model is the following. So whenever you have a document in your corpus of freely available text. So first of all, on the web, for example, sentences are not kind of independent of each other. Like they come in the form of a web page or a document, right? So there is a structure between the sentences on the web, right? So what we can do is the following. So we can get any pair of sentences that come near each other, sentence one and after that sentence two. We can give sentence one to the encoder, and then we can use the decoder and with the language modeling objective, the next word prediction objective, to train the whole model. So the supervision can come from this this language model next token prediction in the decoder. So that's one way to do that. And in fact, this is an objective which is based on conditional generative modeling viewpoint to encoder decoders. So the encoder kind of encodes the conditioning context, and the decoder generates the tokens of the sentence one at a time. So that's one way to do that. But there are other ways to do that as well, which are usually more interesting. So in T5, which is one of the important models by Google, what they do is the following. So they take an original text, like "thank you for inviting me to your party last week," and then they mask out some spans, for inviting is masked out, last is masked out as well. And then each span is replaced by a dummy kind of token or dummy special token, think of these dummy special tokens as variables like X and Y. And then that input which is masked with masked out spans and and with these special tokens, this sequence is the input to the encoder, thank you X, me to your party Y week, that's the input to the encoder. And the target in the decoder is for each kind of a special token, what are the words to fill that span, X should be filled with for inviting, and Y should be filled with last, right? So the decoder should produce this sequence here. So and yeah, and then that's the training objective for training this encoder decoder. So the encoder decoder in T5 is is trained by filling out by masking out the the input sentence and expecting the model to kind of fill out the spans, right? So this model is trained based on single sentences, right? So we don't need paired sentences. All right, let me move on from T5 to another very important model, which is called BART, and this is based on the denoising idea. Like the input is noised, and then the output is the denoised version of the input, and that's how this training objective works. So like for example, in the input, you might have some of the words masked out, like a you see these placeholder positions, and in the output you want in the decoder side you want the full sequence to be generated. So the input could be a placeholder B, placeholder E, right? And then the output should, in the decoder should be A, B, C, D, E, right? So the decoder should be able to generate and denoise the input. So in some sense, it's similar to T5, but the difference is that in T5 they are interested in the output. They are interested only into generating the tokens for the masked spans, but in BART they are interested in the output. They basically generate the full correct sequence. So masking tokens or spans is not the only noise that they kind of apply to the sequences, to the sentences on the web, to the sentences on the web for the input. There are other ways of injecting noise as well. So for example, if you give me like the sentence A, B, C, D, E, like they do a permutation, right? And then the permuted version of the sentence is the input to the model, and then the output is the correct order A, B, C, D, E. If you have multiple sentences in a document, another perturbation or noising operation is permuting the sentences, right, without changing the tokens in the sentences, and then concatenating all of those permuted sentences as one super sequence, giving it to the BART, and then requiring BART to produce the correct ordering of the sentences. So that way, BART learns, like what we refer to in linguistics as the discourse. So sentence permutation, like the kind of information that it that denoisings of permuted words of single sentences, the kind of information or a skill that it allows BART to learn is the syntax, right? So and language modeling. So it needs to kind of learn what the ordering of words are good, which, as we saw before, it's something that language models should do. And it has the token masking noising as well. Like it's similar to the masked language modeling in that sense, and spans as well, so which is similar to the task that we saw for SpanBERT. Anyway, so these are the different noising operations that are in BART, right? They can be mixed together as well. Like you can permute and you can mask out, to build like more more difficult and harder puzzles for BART in the training time. Okay, so after like pre-training the model this way, they then used the model for downstream tasks. Like, for example, if you have a classification task, like, if you want to classify sentences for their sentiment. So what they do is that they give, like, the sentence A, B, C, D, E to the encoder. And they also give it to the decoder, which is like, the model doesn't generate actually anything new. It only needs to generate what it is expected to generate, which is the input. This is something that we call forced decoding. And then, like, after the forced decoding, the model, you can get the embedding of the last time step in the decoder as the representation and build your classifier on top. Or you can represent the label as a token and require the decoder to generate that token at the end. So it's basically classification as generation. So that's also a very important idea. And that idea is similar to prompting, right? So anyway, so that's the classification setting of using BART. We can use it for machine translation as well. So the idea in basically machine translation is the following, if you want to use it. So you put, like, let's say you want to translate from Chinese to English. You put an encoder which is trained on Chinese, which is this yellow thing, right, on the Chinese sentence to encode the meaning of the Chinese source sentence. And then the output of that goes to the input of the encoder of BART, and the output of BART, and then the decoder in BART actually generates the translation. So the idea is that, this yellow kind of, let's say, encoder in Chinese does the understanding of the Chinese sentence in a semantic space which is the same as the semantic space of this encoder of BART. So in some sense, like, this does act like a dictionary, like, to translate Chinese words into English words. And then, the job of the decoder in BART is to do then the reordering and produce a fluent English translation. So yeah, dictionary, like, and then reordering. All right. So this is how a machine translation can be built.
Sorry, can you take a look at the chat box? There are some questions.
Yeah. Sorry, I couldn't actually see these ones because I'm using, the browser version. Maybe, given the time, we can go ahead and then I can come back to the questions. Is that all right?
Oh, sure.
Okay, thank you. Thanks everyone for your patience. Because we started a bit late, I kind of think that let's go ahead and then we can come back to the questions. And also, like, at the end, like, if we don't have enough time for question answering, please feel free to send your questions by email and I try to answer them as soon as I can. So the next version of BART is called MBART, like multilingual BART. So what they did is two differences to the BART that we just saw here. So one is that instead of only English, they used monolingual text in many languages, right? So, in other languages as well. And also, like, they found that, only two noising operators are sufficient. They don't need to have like all of them. Like span masking and permute are the ones that they selected. So yeah, so if you have a bunch of monolingual documents or corpora in multiple languages, you can basically train a multilingual encoder decoder this way. And then they showed, like, that this is really good in machine translation. And in fact, in our group, this MBART is the backbone of some of the some of the kind of translation systems that we built for some of the, competitions, and it has worked very well. Okay, just to summarize these large language models, we saw that some of them are trained like based on the left to right as language models, as normal language models. Some of them are trained, these are the decoder ones. The encoder ones are trained based on the masked language modeling, like masking a token and then requiring the model to predict it. And then the encoder decoder at the end, like was based on the denoising objective. You define some kind of perturbation operation to perturb the sentence and then require the model to predict the correct version of the sentence in the training time. And then there is this prefix LM as well, where this is another setting based on which the decoder ones can be it's a mix of encoder decoder, where if you have pairs of sentences like X and Y, you basically give X to the model, and the model actually looks like a BERT encoder, like when it encodes X, and then after X, when it gets to Y, the model needs to generate Y one token at a time. So this is like called the prefix language model. And yeah, so I didn't specifically cover this, but it's very similar to the other ones. I mean, you can imagine like the objective function for this as well. All right, but for more information, please go into the paper down there. Okay. Now let's look at some of the other issues or other factors when dealing with large language models. The first one is the size. Okay, the larger is the better. So in the x-axis, you see the size of some of the language models in terms of the number of parameters. And in the y-axis, we see the translation quality. The higher is the better for some of the language pairs. And as we can see, like, as the size gets larger, like the quality of the translation gets better. Okay, so it's better to kind of go as, go larger, but to what extent, right? So there are these series of papers which actually discuss, like, what's the asymptotic, like, in terms of the size, for example, like, what would be the behavior of the improvement of the loss function in terms of the size, for example, as we grow the size, which is this plot at the end. Or it could be the data set size. What would be the asymptotic of the behavior of the loss curve as we use more data set, or even like as we use more compute to in optimizing the model. So they show that the empirical performance of these plots show a power law relationship of the loss function with each of these individual factors, compute, data set size, and parameters, right? So and then what they did is that they found the coefficients of this power law kind of formula, which relates each of these factors to the loss function. And they have done, there are a few papers on this, like, for language models, for encoder, like decoders, and for encoder decoders, etc. You can basically have a look, but this is like, the paper which has started this line of thinking. Okay, so the next topic that I want to cover is the deep transfer learning, right? Once we have these pre-trained language models, like, what can we do with them? I kind of alluded into some of the uses that we can have, but I go in more depth here. So, so we saw that, the basic motivation of GPT and then T5 and many of these language models is to kind of treat many NLP problems with only one model. So, and then the usual kind of practice is to get your model, attach some additional parameters into, on top of it, and then, fine tune it into, based on the data from the target task of interest. So, and then this is called the transfer learning, right? The question is that, can we do better? Again, can we do a better transfer learning? And that's the question that we want to address in here. So the first paper that I want to discuss is from this year's ACL. It's called Parameter Efficient Transfer Learning with Diff Pruning. So the idea is that, is very simple. They say that, suppose the parameters of the language model, the pre-trained language model, are denoted by theta pre-trained. So they say that if we kind of fine-tune this pre-trained language model on the data from the target task, right? We can denote the differences of the fine-tuned model with the original parameter setting by delta. Like delta is that vector of differences that we need to have, with respect to the initial parameters of the language model to get the, task-specific parameters for the language model. So what they do is that they try to impose a sparsity of these delta values, right? And when they impose a sparsity, it helps kind of to not store the full language model parameters, right? And only the deviation vector, which, if it is sparse, it needs like a, smaller space to encode it. And for some kind of settings, having this, ability to kind of represent the model with compactly is important. So that's from requirement perspective. And also they show that, it leads to good performance as well. And you can look at the table that they have. All right, and this is this shows the pattern of sparsity, so I don't go into that, but I think you got the idea, right? So that's a really cool paper. The other paper that I want to discuss, or the line of work I want to discuss, is the notion of adapters. So as I mentioned, as one motivation for this diff pruning paper. So one of the important requirements in many situations is that we don't, we want the language model to be further kind of adapted or fine-tuned somehow to the target task of interest, but for some reason we don't want to kind of change many parameters, right? So with diff pruning, explicitly the sparsity constraint, it was imposed on the delta, the delta vector. By sparsity, I mean, it was encouraged, in the training time by some functions working on the delta vector, for it to have many zeros. So many zeros means, it is what I refer to by sparsity, and only a few of the weights should have a non-zero delta. Right. So another way of basically limiting the number of parameters that need to change is from another perspective. So in here, what you do is that you get your pre-trained model, let's say BERT, and you add a few parameters in a very careful manner to the architecture of BERT to basically adapt the whole kind of encoder to the target task of your interest without changing the parameters of BERT, right? So these carefully crafted parameters are called the adapters. So notice on the left, the standard transformer block in the encoder, like, you have a multi-head attention, feed-forward network, which goes to layer norm, and, and then another feed-forward network, and then layer norm, and then the output, right? So they add these kind of so-called adapter blocks, like after the feed-forward layers, like the first one and the second one. And these adapter blocks have, like, very few parameters. So on the right, you see, like, the zoom in, like the architecture of the adapter, like, which is zoomed in. So the input to the adapter, right, goes to a feed-forward down projection. So a matrix which down projects a high-dimensional input vector to a smaller dimensional output vector, and then it is passed through the nonlinearity, and then another kind of module there does the up projection. So the vector is mapped back to the same dimensionality as the input, and then we have a shortcut from the input to output as well, and then that's it. That's the adapter block. And then in the training time, you learn this feed forward and down projection and up projection kind of layers, right? So, and those are the things that, those are the parameters that are injected carefully to the transform blocks. Okay, so in this ICML paper in 2019, they did that, and they showed that the results are remarkable. For example, if you see this glue plot on on the top left, on the x-axis you see like the number of trainable parameters, right? And on the y-axis you see the accuracy delta, and the orange or kind of red shows the adapter, and the blue shows the the usual fine tuning, like how many parameters are changing. So with a small number of parameters added to the model, like here, for example, you see that the model has has a very good doesn't deviate that much from the best performance that you could get based on fine tuning all of the parameters. And you can look at the other plots as well. So this is the one of the important papers in this area. And then fast forward to from 2019 to this year, 2021, there is this interesting paper in ACL whereby what they did is that they learned how to generate these adapters for different tasks. So suppose you have a task, right? So you want to have this adapter here and here in your transformer block. And this is the architecture inside the adapter. So what they did is that they learned in a hyper network, right, which is what I'm showing here by the mouse. They learned this so-called hyper network, whereby the input to this hyper network is like an embedding for the task, not the task itself, not anything else. And then the output of that hyper network is actually the weights of the adapters, right? And then that way, basically, you can kind of do multitask learning using the adapters, right? So, and what you share actually among the tasks is the hyper network based on which the adapters for each task are generated. Okay, so that's a mechanism for multitask learning. And for more details, you can look at the paper. I'm going to another paper, which is called Adaptive Fusion, a non-destructive task composition for transfer learning. So this is also a very interesting paper. So suppose, you have multiple tasks, right? And for each task, you learn an adapter, right? And suppose you want now to build a multitask model, right? The motivation here is also multitask learning. So how can you kind of combine the adapters learned for these individual tasks, right? So we have, let's say, 3 tasks. So for each task, we learn one adapter, right? And what they do, actually, they put a module on top of these 3 adapters. They call it the adapter fusion module, where the input of the adapter fusion module are basically the output of these different adapters. And then the adapter fusion kind of fuses, the output of these single adapters to produce one output. So that is a mechanism for multitask learning. And for more details, you can have a look on this paper, which is in this year's EACL, like in 2021. I'm looking at the time. Okay, I'm just, all right. Let me go to, you're using adapters for machine translation. So far, I have discussed adapters for encoders, but you can have adapters for the decoders as well. So, if you consider, if you're familiar with the transformer blocks, like they're similar, right, in the encoder and decoder, except the kind of attention and the cross, modality attention. But this, the basic idea is that, or insight is that you can have adapter on the decoder as well. And that helps a lot for kind of generation tasks. And particularly, like, you can have adapters for both encoder and decoder for machine translation and make, multilingual machine translation, like, better. So here is in this paper by Google in EMLP 2019. Here is basically the distribution of the data for different language pairs that they had. And they mentioned that, okay, so we have these different amount of data for different language pairs. And usually, like, what happens is that if you kind of train one model, one encoder decoder model using, the concatenation of all of this data, what happens is that, the translation quality for low resource languages, like, the languages for which you have a small amount of data, gets improved because, they kind of benefit from the data from the large data of high resource tasks. But for high resource tasks, or the ones which have large amount of data, the story is different. Usually, like, what we see is that the translation quality, hurts there. So this multitask learning, or in multilingual NMT, kind of hurts the high resource languages, but helps the low resource languages. And the motivation of this paper was to kind of reduce the hurting of high resource languages. This hurting of performance is also denoted in multitask learning as the negative transfer. So they wanted to kind of reduce the negative transfer. And what they showed is that, by adding these adapters, you can kind of reduce this negative transfer phenomenon that we just discussed. I don't go into the details, but that's what they wanted to do, and they achieved it to a good extent. And this is a resource from which you can actually get adapters for many languages if you're interested in. Let me get to the final part of the talk, which is, I think, very, very important, which are on the social and ethical challenges and the global challenges of large language models. So far, we have seen, like, what these large pre-trained language models are, how we can build them, based on which architectures, based on which objective function. We saw, like, how we can use them for downstream tasks, by deep transfer learning, etc. Now we get into, like, global social and ethical challenges when we work with these models. So the first thing is that these models actually have a lot of CO2 emission, and And that's why, like, we need to be aware of the, of the impact on the environment. So when working with big models, this is, a big problem for environment and becomes very important. The other thing is basically the biases, the potential biases in these models. Okay, so these models are usually trained on uncurated data. I mean, on kind of unregulated data, right? So the data which is freely available on the web or like, other resources. Now, thinking about the web, there are like a lot of data there reflecting like, the different views from the society, right? So, the society, the values in society which generated, or societies which generated this text actually is reflected in the text. Now, if like those values are questionable, then, the data which is produced is questionable as well. And the model that we train based on this data actually shows those behaviors as well. I mean, those questionable behaviors as well. And this is something that we need to be conscious and aware about as well. And sometimes that those the questionable behaviors are signified in the model actually. And this is a really important problem when it gets to sensitive issues. And as the field grows, I mean, one thing is that the field will grow anyways. But the thing is that as engineers and scientists, we need to be aware of our social, ethical, and moral responsibilities, as much as we can, I think. Thank you all for listening to me, and I'm happy to take questions.